One kind of double displacement reaction is the precipitation reaction. And this is where we have ionic compounds, right? Aqueous ionic compounds that react with each other to form an insoluble precipitate, right? And the first thing we have to remember is what are ionic compounds? Remember, they are metals, right, with nonmetals or polyatomic ions. Here's an example of a precipitation reaction. So insoluble products form when solutions are mixed. So remember, what we're seeing is aqueous things react with aqueous things to give us solid and then something else. So this is a classic example. This yellow stuff is lead iodide. So in this case, we're going to talk about three different kind of equations. The molecular equation is the compounds when they react. So if lead nitrate is mixed with potassium iodide, we have lead nitrate, right? This is lead 2 nitrate, so it has a charge of +2. Each nitrate is -1, but we have two of them, so that's a good ionic compound. Sodium has a +1 charge, iodide has a -1 charge from the periodic table. That's a good ionic compound. Lead iodide, so it's still +2 and 2, 1 minuses, and then +1 and -1. Right? Aqueous plus aqueous gives me solid, and in this case, aqueous. All right, and we'll practice writing good molecular equations in a second. The ionic equation, you take anything that is aqueous and you have the ions dissociate. So this is lead 2 ion, so we write that, aqueous. There's 2 nitrates here, right? This means 2 NaIs, right? 2 sodium iodides. So that means 2 sodium ions and 2 iodides. And they give me lead iodide solid, 2 Na pluses and 2 NO3 minuses. The next thing we do is we look at the net ionic equation, where we take away any of the so-called spectator ions. So a spectator ion is any ion that appears exactly the same on both sides of the equation. So 2 nitrates are exactly the same. 2 sodium ions, exactly the same. So these guys are the spectator ions, right? Even though there's 2 of them, we don't say 2 Na pluses are the spectators. It's just Na plus or nitrate, the spectators. And what's left over once you take away the spectator ions is the net ionic equation. And this thing just shows the chemistry, what's actually going on here. It takes away things that just make it more complicated, right? The spectators just make it look messier than it really is. So this is saying that lead 2 plus 2 iodides react to form lead iodide, right? So that's the net ionic equation. We'll talk more about solubility, but basically one thing we have to know is what's going to be insoluble. How do we predict if something's going to be soluble and aqueous or insoluble and solid? And it has to do with lattice energy and solvation energy, how well the ions interact with water. All right, we have some so-called solubility rules for predicting whether something's going to be soluble or insoluble. All right, and let's start down here. So carbonates, phosphates, chromates, sulfides, hydroxides, and oxides are usually insoluble, right? They'll form solids. One thing you'll see about it is many of them have high charges, right? And if we think about lattice energy, remember what gives you a high lattice energy? You want to have high charges, right? So the bigger the charge of the ions, the higher the lattice energy, the stronger they hold each other together. And you want to have small radii. But these guys have large charges, which predicts that they really want to hold on to their counter ions and stay solid, right? So these are mostly insoluble. But then we have some exceptions, right? These guys are soluble. So if you have a compound that has any of the first group, right, the alkali metals, lithium, sodium, potassium, rubidium, cesium, they will be soluble, right? So if your compound contains these guys, it will be soluble regardless of whatever else is in there. Ammonium ions are also always soluble. Nitrates and bicarbonates are always soluble. So if you see, chlorates, sorry, I messed up. If you see any of these guys in your compound, you know it will be soluble and will write aqueous. Halides and sulfates are usually soluble, but there's an extra thing to watch out for. So halides like chloride, bromide, and iodide, if you have a compound with those guys, they're usually soluble unless they're halides of silver, mercury, and lead, right? So AgCl, we'll say. Nope, yeah, AgCl will be insoluble. AgNO3 will be aqueous. Sulfates are usually soluble with the same 3 exceptions and an additional 3 exceptions. So sulfates are usually soluble unless you have one of these 6 cations: silver, mercury, lead, calcium, strontium, and barium. All right, so let's practice using these things. So when you see this magnesium chloride, you remember that chlorides are usually soluble with 6 exceptions, right? Silver, mercury, lead, calcium, strontium, barium. Magnesium is not one of those, so it's soluble. We'll write aqueous. Ammonium chloride, right? Halides are usually soluble with the exception of the 6 exceptions, but ammonium ions are always soluble, so we know he'll be aqueous. Potassium hydroxide, as soon as you see potassium or any of the alkali metals, you know it'll be aqueous. Right? It's here in this mess. Nitrates are always soluble. Halides are usually soluble with 3 exceptions, and they are silver, mercury, and lead. So this guy is insoluble. Carbonates are usually insoluble, and this is not one of the exceptions, right? So this guy will be a solid. Sulfates are usually soluble with 6 exceptions, and calcium is one of those. So this guy will be solid, right? He'll be a precipitate. All right, so now with these rules, we can go back and we can apply them. So here's another example. Here we have calcium carbonate reacting with hydrochloric acid, giving me calcium chloride, water, and CO2. All right, just to check, I wrote solid, so we know it's soluble. Carbonates are usually insoluble. This is not one of the exceptions, so that makes sense. We'll ignore this guy, he's an acid. Chlorides, halides are usually soluble, right, with 3 exceptions: silver, mercury, and lead. That is not one of them, so he's aqueous. All right, so the ionic equation, what do? Right, anything that's aqueous, we split into its ions. So calcium carbonate is not aqueous, so we write it exactly the same. This means 2 H pluses and 2 Cl minuses. It gives me calcium 2 plus. Whoops, I didn't write aqueous these times. Aqueous plus, now this 2 means 2 chlorides, right? It doesn't mean Cl2. So remember, 2 Cl minuses plus H2O liquid, it doesn't change, plus CO2 gas. All right, do we have any spectator ions? It is chloride and chloride, right? Those guys are exactly the same on both sides, so they are spectator ions. So the net ionic equation we rewrite without the spectator ions. Liquid plus CO2 gas. All right, and the spectator would be chloride. Yeah, one more. So let me say this one more time because it's important. This 2 here becomes a 2 in front, right? So don't write this. That's crazy talk. All right, let's see. So this is the next level. This is as complicated as it gets. So write the net ionic equation for the reaction that occurs when aqueous barium chloride reacts with sodium sulfate. All right, so there's 4 steps to doing this. The first step is just write the elements together. So barium chloride plus sodium sulfate, right? You need to spend a little time going over your polyatomic ions. And we know it's a double displacement reaction, so let's switch partners. Barium goes with sulfate now, plus sodium goes with chloride. The next thing to do is to make the ionic compounds correct. So remember, the charges have to cancel to give me a neutral ionic compound. So from the periodic table, barium is in the second group, right? The alkaline earth metals, so he is +2. Chloride is a halogen, he's -1. Sodium is +1. Sulfate, we have memorized, is -2. +2, -2, +1, -1. Okay, so using that, we can see that +2 and -1 don't cancel, so we need a 2 here, right? So to fix ionic compounds, you put the subscripts in. Na plus and -2, that doesn't work, so we need a 2 here. Barium sulfate is good, +2, -2, and sodium chloride is good. All right, so first step, we just put the elements together. Second step, we balance the compounds to make them good, right? Make sure their charges cancel. Third step is balance the equation. And I have 1 barium and barium, that's good. I have 2 chlorides. Whoa. Here I need a 2 in front of here. Now I have 2 chlorides. I have 2 sodiums coming back here, 2 sodiums, a sulfate and a sulfate. It's balanced. Nice. Next step. So this is the molecular equation. Next is the ionic equation. What do? Oh, we got to go back and do some stuff here. So we got to think about our solubility rules. So halides are usually soluble with 6 exceptions, and this is not one of them. Yeah. Oh, so I said that wrong. Bad work by me. So halides are usually soluble with 3 exceptions: silver, mercury, and lead. And barium is not silver, mercury, and lead. Oh boy. So this guy is aqueous. He's soluble. Anything with sodium in it is soluble. Barium sulfate. So sulfates are usually soluble with 6 exceptions, right? You say them. Right. Silver, mercury, and lead, calcium, strontium, and barium. So this guy is an exception. He's solid, and sodium chloride will be aqueous. All right, so we can see it's a precipitation reaction where we've made a solid precipitate. So the ionic, then, we got to split our compounds into their ions. 2Cl minus plus 2 Na pluses. Oops, aqueous, plus sulfate. I'm going to write a barium sulfate solid plus 2 A plus 2 Cl minus. So I just rewrote everything that was aqueous and as separate ions. And remember, subscript 2's become coefficients in front, right? This is a 2, so this 2 is carried over for both of them. All right. It makes sense if you remember these things are atoms, right? All right. Do we have any spectator ions? I think we do. Chloride is a spectator. Sodium is a spectator. There we go. So the net ionic equation is barium 2 plus sulfate gives me barium sulfate. Nice work by us. All right, so those are precipitation reactions. A lot of little things to review. We've seen a lot of this before, but we have to write good ionic compounds, so we need to know our charges of the ions. We need to know our polyatomic ions. The next thing we've learned is the solubility rules. So you need to spend some time and make sure you know those so you can predict that things will be soluble or insoluble. And then finally know the difference between molecular equation, ionic equation, and net ionic equation. Acids and bases are next.